My name is Carl Pearson, and this is the HPDC 21 presentation of TEMPI, an Interposed MPI library with a canonical representation of CUDA-aware datatypes. I'm a postdoc at Sandia National Labs right now, but this work was done during my PhD at the University of Illinois with my colleagues there at IBM's T.J. Watson Research Center and my advisor, who's now at NVIDIA Research. So I'm going to motivate this work by talking about sort of distributed GPU stencil style code and sort of the non-contiguous data concerns that come with that. And this relates to the message size in MPI, and also MPI provides something called derived data types, which allow you to describe non-contiguous data to MPI directly and have MPI operate on it. So this sort of introduces a particular challenge, which is that using MPI-derived data types, there's many different ways to describe the same non-contiguous data. And so to be user-friendly, the MPI implementation should treat equivalent non-contiguous data types equivalently. And we do something called that I call translation and canonicalization to recognize and handle that case. Thirdly, we observe that the GPU communication methods are not all created equal. That is to say, there's different ways to get the data from the GPU to the CPU or between GPUs. And we develop a simple performance model to automatically determine that for each individual MPI communication call. And then the final piece of the puzzle is how you actually evaluate these changes on a real system. And so we create an Interposed library implementation that we can evaluate on the Summit system at Oak Ridge National Lab. Just for some context, this is what a sort of traditional accelerator supercomputer node looks like right now. So this is OLCF Summit. It's got 6 GPUs and 2 CPUs. And so it's important to use those GPUs for the compute portion of your application. Stencil codes are at the core of many applications, and these codes will distribute their grid point data across many GPUs after doing some kind of regular spatial decomposition. So in this case, right, I've drawn some 2D images on the slide. But basically, every GPU grid needs to communicate part of its boundary region with its neighbors, but due to the one-dimensional data layout, some of these dimensions are contiguous in memory and some are not contiguous in memory. And so when we're talking about moving data between different GPUs, in some directions we would be moving a few large blocks to cover these halo or boundary regions, and in some directions we have to move many small contiguous blocks. And of course, the reason that that's a problem is due to the latency of the MPI implementation on Summit. So basically, I'm just picking the CPU numbers here as an example, but the GPU transfer numbers kind of similar. So basically, you can see that if we're on the left side when we're sending small amounts of data, the latency is relatively short, but really the effective bandwidth is much higher when we're sending larger messages. So you can see that here we're sending 30,000 times as much data, and it's only 80 times slower. So if we have lots of data to send, we really want to be sending as large messages as possible, not the small messages that the non-contiguous memory would cause us to send. And so sort of the traditional way to handle this with a CUDA-aware MPI implementation is you have sort of a packing step. So on the sending side, the first thing you do is you take your non-contiguous data and you pack it into a contiguous buffer before you send it to the receiver, who then has to unpack it. And so we'll write these packing or unpacking kernels in CUDA, say, by hand. But MPI, as I mentioned, has a facility where we can handle that, where MPI can handle this for us. So basically, we can tell MPI about the non-contiguous layout of our data, and then we can directly operate on those non-contiguous types. So here we just have an example of using MPI type contiguous, MPI type vector to build up, sort of an arbitrary 3D region. So, one of our stencil halo exchange regions in MPI. And then our process is simpler. Sort of in the setup phase of our application, we'll use those MPI functions to describe our type, And then each halo exchange, all we have to do is do, the send and receive, which can operate directly on those non-contiguous types. And so, one way we could build this up into a halo exchange is we could have a phase where we pack all of our data, and then we could have a phase where we do communication on those packed buffers, and then we can finally have a phase where we unpack those packed buffers that we've received into our three-dimensional structure. And so the reason we break up the code like that is so it's really easy to tease out sort of what share of the performance we can blame on the pack versus the communication versus the unpack. And so on this MPI implementation that's on Summit, what we see is that the packing and unpacking dominate the total application or total exchange time by several orders of magnitude. So here we can see that the pack and unpack are both 500 times slower than the actual packed communication. And so this basically forces people to write their own pack and unpack kernels instead of using the MPI interface to handle their non-contiguous data for them. So the reason this happens is that in the MPI implementation, they correctly identify that you want to be sending large contiguous blocks across the network, but the creation of those large contiguous blocks itself uses many operations on many small blocks. So in this case, I'm showing 4 small blocks being combined to a large one, but in actual application, you might have millions of these CUDA memcopy async operations on millions of small blocks. So what many MPI implementations do to correct this problem is they will, instead of launching many small operations to handle the non-contiguous data on the pack and unpack side, they will launch a single larger operation that's accelerated by the GPU's compute to pack and unpack the data. And so then we're solidly in the bandwidth regime for all of these operations. And this is also the foundation of how TEMPI works. But what we observe is that there's many different pathways to get to the semantically equivalent destination when you're describing this to MPI. So I've shown just sort of a couple options here. So we can build a plane of rows or a plane of columns, or we can skip some of these steps directly through MPI. And so depending on what you do here might depend on how your application was constructed or what kind of data it's meant to represent. But the problem is we could potentially have to write one kernel for each of these pathways, or maintain one kernel in our MPI implementation for each of these pathways for the pack and unpack side. And so that's sort of a challenge for maintainers and also for potentially introducing future MPI data types. And so what we do in TEMPI is when MPI type commit is called on one of these types, we have a translation and canonicalization step that basically discovers a compact representation of any semantically equivalent data type so that we can then operate on the canonicalized data type regardless of how that data type was described to MPI. And then based on that, we launch particular kernels to handle the results. So the core of TEMPI is built around this internal representation, which is basically a hierarchy of different strided repetitions of bytes. So at the bottom of this representation is a dense data, which represents a contiguous block of bytes, and then on top of that we can add sort of nested, non-contiguous repetitions of the child type below it. And so in this way we can represent any regular strided type that's been described to MPI. This is just an example of if we use several vectors to build up a 3D type, what the hierarchy of the type looks like. Since each vector is a repeated sequence of blocks of child elements, each vector maps to 2 stream datas. So when we use a vector to build up the rows, then the planes, then the cuboid, we actually end up with 6 stream datas instead of 3. So the next step is to basically recognize that the different ways that you describe data types to MPI are actually describing some semantically equivalent data type. And so we have a set of transformations on the IR. So basically we repeatedly apply these canonicalization operations until the IR no longer changes. And then we've arrived at the canonicalized IR. And so quickly, basically, there's a couple in these transformations quickly. The first is recognizing that we might have a stream of dense data where actually it could be represented just as a single dense data, just based on the parameters of the stream. It turns out that all of the child elements are contiguous in memory. The next one is if you have a stream data of count 1, and this commonly comes up if you use MPI vector with a block size of 1. And so we basically want to get rid of the stream that has only a single element in it that doesn't add any semantic information to our representation, so we can just delete it. And then sort of the third major operation is recognizing, say, for example, if you have 2 vectors of 3 elements versus 1 vector of 6 elements, those are equivalent. So you can detect that transformation and flatten it to as few hierarchy elements as possible. And then the final element is sorting, which basically handles the case if you decided to do a column of rows, say, instead of a row of columns. So we can normalize that case as well. And so then once we've arrived at this, we dispatch for each dimension of data, there's an optimized kernel. So if you have 2-dimensional data, there's a kernel, 3-dimensional data, there's a kernel, and so on. And so the parameters for that kernel are basically determined by the canonicalized IR. So since we do some operations at MPI type commit time, we evaluated how much time we add to MPI type commit operation, and so you can see that we take it from essentially free, because Spectrum MPI didn't do any optimization at that time, to several microseconds of latency. But this is the kind of operation that we expect to be done rarely in an MPI code, so this is probably tolerable for most iterative codes. And basically the result is that we can sort of investigate the direct effect on the pack by on the non-contiguous data handling by just looking at the time it takes to do MPI pack without any communication. And so you can see that in red is MPI pack when TEMPI is used. And we, depending on how non-contiguous the input data was, we do from an order of magnitude better to Spectrum MPI to 5 orders of magnitude better than Spectrum MPI. And so of course we're interested in communication and not just MPI pack. And so we also observe that there's several ways to get the data between GPUs in these MPI systems. So the first sort of baseline method is here. If you just use Spectrum MPI without any changes, you have some non-contiguous data, you give it to MPI send, and you call MPI receive, and then somehow that data appears on the receiving side. Then there's a one-shot method, which has been described in prior work, which is basically where you map some amount of the GPU memory, of the system memory, onto the CPU, so the GPU can directly operate on it. And so the kernel that packs the data into a contiguous buffer, that packs that contiguous buffer directly into the CPU memory. And so this introduces some new parameters that we're calling the time it takes to pack into the CPU and the time it takes to unpack into the CPU. And then the final method is where instead of packing directly onto the CPU, we pack into the GPU memory, and we call a CUDA-aware MPI operation on that GPU memory. And so since that's a CUDA-aware MPI operation, it's going to have some different data transfer characteristics than the previous version. And so this is basically our performance model that lets us, based on those parameters, we can basically decide which of these methods we want to use. And so I didn't describe the staged method. It turns out you can see the paper for a little more detail, but it turns out on this particular platform it never is better than the other two. The only trick then is that there needs to be a one-time system characterization step where we measure the inputs to that performance model. And those inputs take 2 forms. One of them are these bulk transfer methods where we're sending contiguous data and the performance just depends on the number of bytes transferred. So here we have device to host and host to device for CPU and GPU. And then we also have the MPI times for CPU to CPU and GPU to GPU. And then the pack and unpack operations, depending on the method, their latency depends on the total amount of data that's being packed or unpacked, since that affects the GPU occupancy, and also the size of the contiguous blocks that are being packed and unpacked, since that affects the efficiency of the GPU memory subsystem. And so we can look at how these methods stack up against each other by doing a ping pong in MPI send. And so basically what we're showing here is for different sizes of objects, each group of bars, each triplet of bars is a different number of contiguous bytes within that object. And you can see that for the larger objects, the one-shot method's better. For the smaller objects, the device method's better. But by evaluating the performance model, we can discriminate between these two accurately, even when the performance between the one-shot and the device is quite close together. So as you can see there on the right in the 4 megabyte site. And this includes the time that it takes to evaluate the performance model itself. And so when we add all these things together, the green is the baseline time, and those 3 other colors are the automatic communication selection as well. And so you can see the vast majority comes from the improved data type handling, and we get a small amount of additional improvement from selecting whether we do the one-shot data transfer method or the device data transfer method. And so when we apply this to an actual halo exchange, this is a 3D halo exchange motivated by a real piece of work or a sort of real application that's cited in the paper. You can see that now the packing and unpacking time is relatively fast, and most of the exchange time is actually just controlled by how long it takes the MPI implementation to move the data between nodes, as opposed to packing and unpacking it on the source and destination side. And at the end of the day, for 3072 GPUs, we're looking at around 1000x speed up for this particular communication pattern without any modifications to the application code. So one interesting challenge here is that we don't have administrator access to Summit, right? OLCF Summit, we're just users. So these large-scale systems are pretty tightly controlled. And often you don't have access to that many MPIs on the system. If you're lucky, you've got 2. And these MPIs are rarely bug fixed, and even more rarely are new features added, right? And so basically it's very difficult for most folks to make experimental modifications and evaluate them at scale in real applications. But MPI has a very well-defined standard, and so we can take advantage of the fact that it has a well-defined standard and how the operating system loads libraries to inject our experimental modifications to MPI, which is what we did for this work. So basically, in our real application, right, I mentioned this before, you just call MPI send on your non-contiguous data and somehow it gets to the receiving side. But basically what TEMPI does is it will provide an alternate implementation of MPI send, which first packs the data in the way that I've described, and then we'll still rely on the system MPI to ultimately do the inter-process communication. And so TEMPI is basically a transparent interposer, a transparent layer interposed between the system MPI and your application. So this is how your application doesn't need to be modified. So typically when we compile an MPI application, we'll have some source code, say in box 1, right? We'll apply our compiler to it. And if you use MPI-CC, basically it's just a wrapper around your C compiler, which is going to include certain file or add certain include paths and link certain libraries. And then that will create a binary in box 4, and basically that binary will have calls to some MPI functions, like say MPI init. And when MPI init is called, the operating system will see that it needs to go search for MPI init in all of the libraries that your application is linked against. And since your application was linked against the system MPI library, it will find MPI init in the system MPI library there in box 5. And that's how your application will start to execute the MPI code. So what we do in TEMPI is basically we compile an alternative MPI library that exposes some subset of the MPI implementation, and we somehow insert our library before the system MPI library in the compilation order. So you can either relink your unmodified application, or you can use something like the LD preload mechanism to inject TEMPI first in the link order. But basically what happens then is your application, when say MPI init is called, it will discover that TEMPI implements MPI init, and it will begin executing TEMPI code. And then internally in TEMPI, we can do whatever we want to do. And then ultimately, as we need to rely on the system MPI for anything that we don't implement or don't care to experiment with, we can call from TEMPI automatically into the system MPI so that your application observes no changes in how correct the code is. So basically, we've showed that this canonicalization approach works well for handling various different MPI data types. We got a lot of speed up on some unmodified on an unmodified application on OLCF Summit, and it works for any sort of regular strided data type. We showed that you can use a relatively simple performance model with some characterization of the target platform to at runtime make selections about the DPU data transfer method, and so that gives a little bit of additional speed up. And this general approach seems to be nice for deploying MPI experiments and prototypes without having privileged access to an experimental platform. So basically, as long as you have supercomputer time, this will work for you. You don't need to talk to the system administrators. You're not modifying the deployment on the computer. Other MPIs have various complete or incomplete strategies for handling non-contiguous data on the GPUs. Obviously, if those implementations provide good performance for you, probably not using TEMPI is the right move, right? But I think it would be useful for the community to have a sort of impartial comparison of the MPI data type performance in some of these implementations. Just since GPU accelerated computers have become so common. And so this code is liberally licensed and available on my GitHub account if you're curious or want to look at how it works or try it yourself. So thank you.